Hello, I am Shravani. Today we will be looking at the theorem of corresponding states and reduced properties along with the numerical. First, we will find what the compressibility factor means and look at compressibility chart. Then we move on to the principle of corresponding states and the other equations of state, finally followed by a numerical example. The compressibility factor measures the deviation of a real gas from an ideal behavior. It is defined as Z is equal to PV by RT. It is the ratio of volume of a real gas at a set of specified temperature and pressure, the volume occupied by the gas at the same temperature and pressure if it were an ideal gas. The compressibility factor of a perfect gas has the value of unity at all conditions. Since a real gas behaves ideally as pressure is reduced, the compressibility factor of a real gas approaches unity as the pressure is reduced to zero. Compressibility charts, as shown on the screen, which is the compressibility chart of nitrogen, can be drawn for different substances. The use of such charts, however, for practical applications is very cumbersome and they serve little useful purpose when compared with a generalized chart applicable for all gases. In fact, such generalized compressibility charts, as seen on the screen, are made correlating the pressure, volume, and temperature behavior of all fluids based on the principle of corresponding states. The principle states that all gases, when compared at the same reduced temperature and at the reduced pressure, have approximately the same compressibility factor and all deviate from the ideal behavior to the same extent. The critical properties are used as a basis for setting up a scale for comparing the properties of substances. The reduced variables are obtained by dividing the actual variables by the corresponding critical constants. Any two gases have the same reduced properties if they depart from the corresponding critical points by the same degree. The corresponding factor of any single component substance is thus a function of two properties, usually the reduced temperature and the reduced pressure. It is represented mathematically as shown on the screen. However, it should be noted that this principle is only an approximation and it works best for gases composed of spherical molecules. For non-spherical molecules and for polar molecules, it fails. The significance of this principle is that it enables one to coordinate the properties of a range of gases to a single diagram such as the generalized compressibility chart. The generalized compressibility chart is constructed based on the principle of corresponding states. On these charts, the compressibility factor Z is plotted as a function of reduced temperature and reduced pressure. Thus, these provide one of the best means of expressing the deviation from ideal behavior. When precise equation of state is not available, these charts provide a convenient method for the evaluation of compressibility factor. There are two other equations of state which are as seen on the screen. The first one is the van der Waals equation of state, which was one of the earliest equations of state given. The other one was the cubic equation of state. So the numerical example is as seen on the screen, where the density of propane is given as 150 kg per meter cube at a temperature of 400 Kelvin and a pressure of 40 bar. The pressure at which butane has the same density at 450 Kelvin has to be found out. So firstly, the reduced state for propane is found out. And for butane to have the same density, which is a dependent property, it must be a corresponding state. Therefore, it implies that butane has the same reduced temperature and the reduced pressure as propane. So then, the required pressure for butane is calculated using the mentioned formula. So according to the theorem of corresponding states, butane will be in a state corresponding to propane state and will have density approximately 36.7 bar using the corresponding states principle. So the references used for this presentation are as seen on the screen, which are both textbooks one by K.V. Narayanan and the other by Pramod Kumar. Thank you.